Hello, my friend. Tonight we're going to explore the universe together, slowly and calmly. Each chapter will guide you through the vast scales of space and time, from stars that live for billions of years to horizons far beyond what we can see. This isn't just science explained, it's science told in a way that helps your mind unwind. If you're new here, know that these videos are designed to both teach and help you rest. So settle in, get comfortable, and let the rhythm of the cosmos quiet your day. Let's begin. Chapter 1. Stars live and die on timescales beyond imagination. When you step outside on a clear night and lift your eyes to the stars, you are seeing events that unfold across spans of time that no human mind can truly hold. Each point of light is a furnace, a balance between gravity and nuclear fusion, existing on scales that stretch billions or even trillions of years. Against such a backdrop, even the rise and fall of civilizations is a fleeting flicker. To understand this, we need to look closely at what stars are, how they are born, how they live, and how they die. A star begins its life hidden from view, deep inside a giant molecular cloud. These clouds, scattered across galaxies, are cold and dark, composed mostly of hydrogen and helium, with small traces of heavier elements. They appear opaque because fine dust particles scatter and absorb starlight, keeping the gas chilled to only a few tens of degrees above absolute zero. In such conditions, pressure is too weak to resist gravity, and clumps begin to form. A passing shock wave from a nearby supernova, the tidal forces of galactic rotation, or the density waves of a spiral arm, may act as the trigger. Once a clump grows dense enough, gravity takes over completely. As the gas collapses, gravitational energy is converted into heat. The center grows hotter and denser, forming a protostar. At this stage, it is not yet shining with nuclear fusion, but glows faintly in the infrared, hidden behind a cocoon of gas and dust. Around it, a rotating disk forms, the raw material from which planets may one day arise. This phase may last a few 100,000 to a few million years, long in human terms, but just the first breath in a stellar lifetime. When the core temperature climbs to about 10 million degrees Celsius, something extraordinary happens. Hydrogen nuclei, protons, gain enough energy to overcome their mutual repulsion and fuse into helium. This process, the proton-proton chain, is the primary energy source for stars like the Sun. In more massive stars, fusion proceeds through the carbon-nitrogen-oxygen (CNO) cycle, a more temperature-sensitive chain that uses heavier nuclei as intermediaries. No matter the path, the outcome is the same. Energy is released in the form of photons and neutrinos, and the balance of forces is transformed. Fusion provides an outward pressure that resists gravity. If the star contracts slightly, the core heats, fusion rates increase, and pressure pushes back. If the core cools, fusion slows, pressure drops, and gravity compresses it again, reheating it. This feedback acts like a thermostat, stabilizing the star for millions to billions of years. Once fusion begins, the protostar becomes a main sequence star, the long and steady phase that defines most of a star's life. How long this stable period lasts depends on one factor above all: mass. Massive stars burn brightly but briefly. An O-type star, dozens of times the mass of the Sun, may consume its hydrogen in just a few million years. They are like cosmic fireworks, brilliant but short-lived. At the other extreme, red dwarfs, which contain less than half the Sun's mass, burn their fuel so slowly and efficiently that their lifetimes stretch into trillions of years. They are the misers of the cosmos, converting hydrogen into helium at such a careful pace that none have yet reached the end of their lives. since the universe itself is only 13.8 billion years old. Our Sun, with a mass that sits comfortably between these extremes, will enjoy a main sequence lifetime of about 10 billion years. Already 4.6 billion years old, it is middle-aged, steadily fusing hydrogen into helium in its core. Each second, it converts about 4 million tons of mass into energy, radiating it outward as the sunlight that sustains life on Earth. Despite this staggering figure, the Sun has only used up a fraction of its fuel. Eventually, however, hydrogen in the Sun's core will run low. Without fusion to provide pressure, gravity will gain the upper hand, compressing the core and heating it further. Fusion will shift to a shell around the core, releasing even more energy. The Sun's outer layers will expand, and it will swell into a red giant, engulfing Mercury and Venus, and possibly even Earth. Its surface will cool and redden, even as its luminosity increases. Inside, the contracting core will reach 100 million degrees, hot enough for helium to fuse into carbon and oxygen through the triple alpha process. For stars of roughly solar mass, this ignition happens suddenly in what astronomers call the helium flash, a brief but dramatic release of energy. Afterward, the star stabilizes again, burning helium quietly in its core for a few 100 million years. But helium, too, will be exhausted. For a star like the Sun, the core will not grow hot enough to ignite carbon. Instead, fusion shifts outward into shells, and the outer layers become unstable. The star will pulsate, shedding its atmosphere in gentle but powerful winds. Over tens of thousands of years, these layers drift into space, forming a glowing planetary nebula, illuminated by ultraviolet light from the hot core. The core itself will contract into a white dwarf, a dense remnant about the size of Earth, but with half the Sun's mass. Supported by electron degeneracy pressure, it can no longer fuse elements, but it will radiate away its stored heat for billions of years, slowly cooling into darkness. Given enough time, it will become a black dwarf, a cold, invisible relic of its former self. But the universe is not yet old enough for any black dwarfs to exist. The fate of more massive stars is far more violent. A star with 8 or more times the mass of the Sun can fuse elements all the way up to iron. Carbon burns to oxygen, neon to magnesium, oxygen to silicon, and silicon to iron. Each stage happens faster than the one before, until the final stages last only years or even days. But iron cannot release energy through fusion. Instead, fusing it consumes energy. When enough iron accumulates in the core, the balance collapses. Gravity crushes the core in less than a second, and protons and electrons combine into neutrons. The neutron star is born, supported by neutron degeneracy pressure. The outer layers crash inward, then rebound in a shock wave. In that moment, the star explodes as a supernova, releasing as much energy as the Sun will radiate in its entire lifetime. The explosion hurls heavy elements into space, seeding future stars and planets with the ingredients for life. If the core remnant is massive enough, not even neutron pressure can resist gravity, and a black hole forms, an object so dense that not even light can escape. Supernovae are destructive, but they are also creative. They spread elements like iron, calcium, and gold through galaxies. Every atom of oxygen you breathe and every atom of iron in your blood was forged in stars and scattered by explosions. Stars die, but their deaths make new generations possible. This cycle has repeated countless times, enriching the galaxy with heavier elements and paving the way for planets like Earth. Astronomers can measure these timescales through clever methods. In star clusters, all stars form at once. By plotting their brightness and temperature on the Hertzsprung-Russell diagram, scientists can see which stars have left the main sequence, revealing the cluster's age. Globular clusters, dense and ancient, contain stars over 12 billion years old, almost as old as the universe itself. White dwarfs, too, act as clocks. As they cool, their temperatures record how long they have been fading. Because the universe is still young compared to the lives of many stars, the distant future will look very different. Red dwarfs will continue burning trillions of years from now, long after larger stars have gone extinct. The last starlight in the universe will be faint and red, slowly dwindling into darkness. In this far future, the cosmos will grow colder and quieter, lit only by the fading embers of stellar remnants. Thinking in these timescales is both humbling and liberating. Human history fits entirely within the middle of one star's life. Every achievement, every struggle, every joy and sorrow all take place within the ongoing stability of the sun's fusion. Compared to the patient glow of stars, our urgency is brief and passing, and yet you are part of this story. The atoms of your body were forged in ancient stars, scattered across the galaxy, and gathered here into a moment of awareness. Your life is short compared to a star's, but no less real. So as you prepare to rest tonight, remember that the stars above you have been shining for billions of years, and they will continue long after your day is ended. They burn with no haste, no worry. You too can let go of urgency. Let your thoughts quiet, as though settling into orbit around calm. The vast, unhurried rhythm of stellar time is here for you. Allow it to wash away the day's burdens and drift gently into sleep. Chapter 2. The universe builds structures larger than galaxies. Stand beneath a dark sky, and a galaxy already feels like the limit of scale. A city of hundreds of billions of stars crossed by lanes of dust and threaded with gas. Yet in the architecture of the cosmos, a single galaxy is only a neighborhood. Gravity, time, and the faint memory of initial irregularities assemble galaxies into still larger entities that span tens to hundreds of millions of light years. These are the structures beyond the individual, groups and clusters, superclusters, filaments, and walls that span regions large enough to cradle thousands of galaxies. The first step above a galaxy is a group. Our own Milky Way does not drift alone, but shares space with Andromeda, Triangulum, and dozens of dwarf companions in the local group, a bound association roughly 10 million light-years across. In groups, the mutual pull of dark matter halos gathers members into a common potential well. Orbits are not neat circles, but tangled paths that remember past encounters. The faint tidal streams wrapped around the Milky Way and Andromeda are stellar signatures of this ongoing gravitational choreography, each stream a fossil trail of a smaller system digested by a larger one. Groups are where galaxies first begin to feel the collective, where interactions and mergers are frequent enough to reshape disks, stir up bars, and alter the reservoirs of cold gas that fuel new stars. Scale up again, and groups blend into clusters, the great metropolises of the universe. Rich clusters can host hundreds to thousands of luminous galaxies, but their dominant mass component is not starlight. Between the galaxies lies an ocean of rarefied plasma, the intracluster medium, heated to tens of millions of degrees and shining in X-rays. This hot atmosphere is a record of assembly. As galaxies and groups fall in from the surrounding web, their motion stirs, shocks, and enriches the gas with heavy elements forged in earlier generations of stars. The temperature and density structure of this atmosphere preserve the energies at play and reveal where recent accretion has sculpted the cluster's outskirts. Clusters allow multiple, independent measurements of mass. The random motions of their member galaxies, read from Doppler shifts, reflect the depth of the potential well. The pressure and temperature of the intra-cluster medium, mapped in X-rays, imply how much gravity is needed to confine such a hot atmosphere. And the slight systematic distortion of background galaxy images, weak gravitational lensing, directly traces the total matter, luminous and dark, projected on the sky. These methods converge on the same striking conclusion. Most of a cluster's mass is invisible, residing in an extended dark matter halo whose gravity binds together the galaxies, the hot gas, and the stars. At the centers of massive clusters sit brightest cluster galaxies, giant ellipticals with extended halos of faint light formed through repeated mergers. Around them, smaller galaxies bear scars of their environment. Some show tails of stripped gas and pockets of young stars drawn into wisps marked as jellyfish galaxies shaped by ram pressure stripping, where the rush of the intercluster medium peels cold gas from a galaxy's disk and chokes off future star formation. Others show distorted shells and tidal debris from close gravitational encounters. Radio maps reveal halos and relics, diffuse synchrotron bright regions energized by shocks and turbulence, evidence that even the cluster atmosphere shares in the drama of assembly. Clusters grow by accreting groups and by merging with other clusters along the avenues of the cosmic web. A cluster-cluster collision unfolds over billions of years. Dark matter halos interpenetrate almost without friction, stars sail past largely unaffected, but the hot atmospheres crash, shock, and separate, drawing luminous bows in X-ray images and lighting radio relics along the shock fronts. In a few dramatic systems, the separation of dark matter from the shocked gas provides a particularly clean view of where mass resides and how different components respond to the same gravitational event. The outskirts of clusters, where infalling material first meets the main halo, show splashback features and caustics, sharp transitions in density and kinematics that mark the boundary between the one-time infalling population and matter that has already orbited and turned around. Clusters do not float in isolation. They gather into even larger associations, superclusters, whose boundaries are better defined by motion than by fixed edges. Our local group and the nearby Virgo cluster belong to a basin of attraction called Laniakea, a region hundreds of millions of light years across, within which galaxy motions flow toward common gravitational centers. The concept of a supercluster is not simply a tally of members inside a drawn contour. It is a pattern of streaming that reveals the underlying gravitational landscape. In this view, superclusters are not rigid objects but coherent regions of flow carved by dense nodes and the filaments that connect them. Filaments are not pencil lines on a map. They are three-dimensional rivers of dark matter and gas extending for hundreds of millions of light years and a few tens of millions wide. Galaxies entering a cluster typically travel along a filament, pre-processed by group interactions before they reach the denser, harsher environment of the core. The gas inside filaments is too tenuous and warm to blaze an optical light, but its presence can be inferred indirectly through absorption features in the spectra of background quasars, and in a few cases through faint emission in soft X-rays. These threads are the supply lines of the cosmos, feeding halos with material that will cool, settle, and form stars, unless and until environmental effects heat and strip it away. The physics inside large structures is as important as their outline. The intracluster medium is hot but not inert. It cools by radiating X-rays, and in the densest cores that cooling would, in principle, cause gas to condense and form stars at prodigious rates. Yet most cluster cores are not ablaze with new stars. Energy injected by central supermassive black holes through narrow jets, buoyant bubbles, and weak shocks stirs and reheats the gas, preventing runaway condensation while still allowing a gentle drizzle of cooling that may feed the black hole and sustain the feedback cycle. In other locations, contact discontinuities called cold fronts mark where gas with different temperatures and histories slides past without mixing, preserving the memory of older accretion events. Not every galaxy reaches the cluster core unaltered. Many are transformed earlier in smaller groups, a process called preprocessing. In groups, the relative speeds are lower and mergers are more common. Gas is consumed or expelled, star formation slows, and by the time such galaxies arrive in the main cluster, they already resemble the quenched population that dominates dense regions. This layered history means that a cluster's census at any moment is a superposition. Some galaxies are newly arriving spirals rich in cold gas and star formation. Others are long resident ellipticals whose fuel is gone and whose stars evolve in quiet aging. On the largest scales, the distribution of clusters and the alignment of their member galaxies encode the recent past of the web. Cluster elongations often line up with the filaments that feed them, and the spin axes of galaxies show subtle correlations with nearby structure. These alignments are not signs of a new force, but the mechanical outcome of anisotropic infall. When material streams preferentially along a filament, it leaves the assembled structure with a memory of that direction. Even the outskirts of clusters carry this imprint, where infall is freshest and substructures are least digested. Large-scale structure is not only a map, it is also a tool. By counting clusters across mass and distance, astronomers trace how quickly structure has grown, and by measuring the subtle preferred separation in galaxy clustering, the fossil of early sound waves, they obtain a standard ruler that helps chart the universe's history when combined with independent probes. Weak lensing surveys, which read the gentle shearing of background galaxies, reveal the otherwise invisible scaffolding of dark matter and anchor these inferences. It is easy, when contemplating such immensity, to forget the tempo at which it evolves. A galaxy's journey from a sparsely populated filament into a cluster core takes billions of years. A cluster merger can last longer than the time since complex life arose on Earth. The curvature of a bridge of gas between colliding clusters might seem frozen to a human life, yet radio and X-ray maps taken decades apart can reveal subtle changes, a reminder that even the slowest stories move forward. The grand architecture we see today is a single frame in a very long film. These structures also shape what happens inside galaxies. Where the environment is denser, star formation is more likely to be quenched, either by the removal of gas or by its exhaustion in earlier bursts. Supermassive black holes in central galaxies are more often active, their feedback regulating both their own growth and the thermodynamics of the intracluster medium. Disks are more frequently transformed into spheroids in the busiest regions, and the familiar morphology-density relation, spirals common in low-density fields, ellipticals favored in cluster cores, emerges naturally from repeated encounters, tides, and gas stripping. Along filaments, by contrast, cold gas can still stream into halos and sustain star formation in galaxies not yet stressed by the cluster's heat and tides. Because the universe is finite in age, we catch these structures at different stages depending on how far away we look. Nearby clusters like Virgo and Coma are mature, with well-settled cores, long-lived substructures, and large populations of quenched galaxies. At greater redshift, we see protoclusters still assembling, their galaxies forming stars more vigorously, their intracluster media not yet fully heated, and their brightest members still building mass through frequent mergers. Farther still, in the first few billion years after the Big Bang, we find the seeds of the web just coalescing, faint overdensities where filaments will later connect and where the first massive halos are beginning to take shape. Not all of the mass tied to a cluster shines in the galaxies we can easily catalog. Tidal interactions unbind stars and sprinkle them into the space between galaxies, building a diffuse intracluster light that forms ghostly envelopes around the brightest members and extends along the paths of past encounters. This light is faint but telling. Its clumps and streams preserve memories of recent accretion events, and its color reveals the age and chemical makeup of stars that were once in the outskirts of spirals and dwarfs, now long dissolved. As one walks farther up the hierarchy, from clusters to superclusters and walls, the names become guideposts rather than strict categories. A wall is a broad, sheet-like aggregation of filaments stretching across hundreds of millions of light years. A supercluster is a dynamically connected basin of flow. The particular examples that draw attention: great walls named for the constellations they cross, basins mapped by the streaming of galaxies, are points on the same continuum. What matters is not the label, but the fact that the universe builds upward. Small halos merge into larger ones, filaments braid into sheets, and nodes at their junctions grow into clusters that continue to accrete material through the present day. There is a quiet thought to carry from this architecture. The universe builds upward from simple beginnings into a hierarchy of forms, not in haste but by slow, patient accumulation. A single galaxy is vast, yet it finds its context in something larger, and that, too, in something larger still. The patterns are not hurried. They are the natural outcome of steady forces acting over long times. As you set the day down, you do not need to hold the whole map in your mind. Let the image of a filament, a river of dim light feeding a distant cluster, be enough. Picture wide spaces and slow flows, gravity doing its work without urgency. Breathe in and allow that steadiness to settle your thoughts. Breathe out and let the noise of the day drain away into the calm between the threads. The night sky is a gentle lattice stretched across distance, and within that lattice there is room for rest. Chapter 3. The universe contains endless oceans of void. When most people imagine the universe, they think of stars, galaxies, and glowing nebulae, bright islands scattered across the cosmic sea. But this picture is misleading, because the majority of the cosmos is not filled with light, or even with galaxies. The universe is dominated by emptiness, immense voids, some hundreds of millions of light years across, where galaxies are rare and space is quiet. These regions are not simply gaps between objects. They are vast components of the cosmic architecture, shaping the evolution of the universe, and reminding us that emptiness is just as real a part of existence as matter itself. Voids were not the first structures astronomers expected to find. For centuries, the night sky seemed full of stars, and when telescopes revealed faint smudges that turned out to be galaxies, it appeared as though the universe was teeming with light. Only in the 20th century, as astronomers began systematically surveying the positions of galaxies, did the true scale of emptiness reveal itself. In the late 1970s and early 1980s, maps of galaxy distributions began to show that galaxies were not evenly scattered, nor even randomly clustered. Instead, they outlined long filaments and sheets, leaving behind immense regions with almost nothing inside them. These regions became known as voids. One of the earliest discovered and still most famous is the Boundless void. Located about 700 million light-years away, it stretches roughly 330 million light-years across, making it one of the largest known voids in the universe. When it was first identified in 1981, it stunned astronomers. Here was a region so large that, if our Milky Way were placed at its center, the nearest large galaxy would lie hundreds of millions of light-years away. Only a handful of galaxies inhabit its enormous volume compared to the thousands or millions expected in a similar-sized region outside a void. The Boundless void was not an anomaly, but an extreme example of what surveys later showed to be a common feature of cosmic structure. Voids are not perfectly empty. They contain dark matter, thin traces of intergalactic gas, and a sprinkling of galaxies, though these galaxies are fewer and often different in character from those in denser regions. Many void galaxies are small and faint, with slower rates of star formation, suggesting that isolation shapes their development. The lack of frequent interactions with neighboring galaxies means they evolve more slowly, undisturbed by the mergers and collisions that shape galaxies in crowded environments. In this sense, voids are laboratories for understanding how galaxies grow when left almost entirely on their own. The existence of voids can be explained by the same physics that shaped the cosmic web. In the early universe, matter was distributed almost uniformly, but with small fluctuations in density. Regions with slightly more matter grew denser over time as gravity pulled more material in, forming filaments and clusters. Regions with slightly less matter, in contrast, were drained of their contents as matter streamed out toward denser areas. Over billions of years, the underdense regions became emptier, creating the voids we see today. They are not passive gaps, but active participants in cosmic evolution, their expansion and evacuation helping define the structure of the web. Simulations of large-scale structure show this process vividly. As the universe evolves, filaments grow denser and more interconnected, while the voids expand, pushing matter outward and making the web sharper. The voids dominate in volume. They occupy about 80% of the observable universe, even though they contain only about 10% of its mass. This striking imbalance means that most of space is emptiness. If you were to select a region of the universe at random, you would almost certainly land inside a void. The bright galaxies and clusters that capture our imagination are the exceptions, not the rule. The physics inside voids is subtle but important. Because voids are regions of lower density, cosmic expansion acts more strongly within them. While galaxies in filaments and clusters are slowed in their outward motion by gravitational attraction, galaxies in voids tend to drift away more quickly, deepening the emptiness. This makes voids sensitive indicators of cosmological parameters, including the influence of dark energy. By studying the shapes, sizes, and dynamics of voids, astronomers gain clues about how the universe expands and how its contents are distributed. The sheer scale of voids can be difficult to comprehend. The local void, adjacent to the local group of galaxies, spans about 150 million light-years. The Eridanus supervoid, another well-known example, may be connected to the so-called cold spot observed in the cosmic microwave background, an unusually cool region in the afterglow of the Big Bang. If this connection is confirmed, it would mean that voids not only shape galaxies, but also leave imprints on the oldest light in the universe. The largest voids rival the size of entire superclusters, stretching across distances so vast that light takes hundreds of millions of years to cross them. Astronomers sometimes describe voids as the lungs of the universe, expanding steadily while filaments act like the bones of the cosmic skeleton. This metaphor captures their dual nature. They are absence, but they are also structure. Their expansion and growth influence how galaxies are arranged, how clusters merge, and how the cosmic web continues to evolve. Though voids are defined by emptiness, they are not entirely silent. The intergalactic medium that threads through them is tenuous but present, a whisper of hydrogen and helium atoms left over from the Big Bang. Occasionally, galaxies wander within these spaces, often dwarf galaxies with irregular shapes, forming stars at a trickle. Their isolation makes them scientifically valuable because they provide examples of galactic evolution unshaped by crowding. Some of the most pristine galaxies known are found in voids, their gas reservoirs relatively untouched by the enrichment of heavy elements common in busier regions. Studying them allows astronomers to glimpse conditions more like those of the early universe. From a scientific perspective, voids are as important as clusters. Clusters tell us how gravity binds matter together. Voids tell us how matter drains away and how cosmic expansion shapes the large-scale structure. Together, they form a complementary picture of the universe's history. Ignoring voids would be like studying a forest by looking only at the trees and never at the spaces between them. Perhaps the most striking realization is that we live on the edge of one. The local group sits at the boundary of the local void, which stretches away into space behind our galaxy. Our cosmic neighborhood, in other words, is partly defined by the presence of emptiness. Without the local void, our motions and those of nearby galaxies would be different. The emptiness itself exerts influence, not through gravity pulling inward, but through the absence of mass, letting expansion run freer. To place yourself mentally inside a void is to imagine an ocean of darkness, where galaxies are so rare that the nearest one lies beyond the range of imagination. The silence would be complete, not the silence of a quiet room, but the silence of near nothingness, with no nearby suns, no planets, no starlight. And yet, from this emptiness emerges the contrast that makes filaments and clusters visible. The universe is defined not just by what exists, but by what does not. This brings us to a subtle reflection. Human lives unfold in a crowded context, crowded with thoughts, with obligations, with moments of joy and moments of difficulty. But the universe itself is not crowded. It is mostly void, and yet it is in the emptiness that structure finds meaning. In a similar way, the quiet spaces of your own mind are not failures but necessary pauses, allowing the patterns of your life to emerge. So as you let yourself rest tonight, remember that most of the universe is stillness and space. The galaxies you admire are rare islands floating in a vast, calm ocean. You do not need to fill every corner of your mind. You can allow emptiness to exist. In that space, worries can dissolve as galaxies dissolve into the quiet of a void. Let your thoughts drift outward, finning into stillness. The day has ended, and the vast silence of the cosmos is here to carry you into peace. Chapter 4. Galaxies drift apart in the expansion of space. One of the most transformative ideas in modern science is that the universe is expanding. Galaxies separated by millions and billions of light years are receding from one another, not because they were thrown across a fixed emptiness by a primordial blast, but because the very fabric of space between them is stretching. This is not ordinary motion across a static stage. It is a change in the stage itself. When you adopt that perspective, several previously puzzling observations align naturally. the systematic shift of distant galaxy light toward longer wavelengths, the way time seems to run slower for far-off events, and the large-scale pattern of matter across the sky. The route to this understanding was observational. In the 1910s, Vestos Slipher measured large redshifts in the spectra of spiral nebulae, at a time when their true nature was still under debate. A few years later, Henrietta Leavitt showed that the pulsation period of Cepheid variable stars reveals their intrinsic luminosity, giving astronomers a reliable rung in the distance ladder. Using those stars to measure distances, Edwin Hubble and collaborators demonstrated in the 1920s that many nebulae were entire galaxies beyond the Milky Way. More importantly, when distances were paired with redshifts, a clear pattern emerged. The farther a galaxy, the faster it recedes. That empirical relationship, Hubble's law, was the first compelling evidence that space itself is growing with time. Because this concept is counterintuitive, astronomers lean on analogies with care. A familiar one imagines dots painted on the surface of a balloon. As the balloon inflates, every dot sees all the others receding, and the separation between any two dots grows faster if they begin farther apart. There is no central dot on the surface. Expansion looks the same from every location. If you upgrade the two-dimensional rubber skin to three-dimensional space and abandon the notion of space as a literal substance, the analogy still captures a key truth. Galaxies are not racing through a static background, so much as keeping their places while the distances between those places increase. Expansion is a large-scale phenomenon. On smaller scales, gravity and other binding forces overwhelm the gentle stretch of space. Atoms hold together under electromagnetism. Planets remain in orbit around their stars. Stars are bound inside the deep gravitational wells of galaxies. Even on intergalactic scales, gravity can win. The Milky Way and Andromeda are on a slow collision course and will merge in roughly 4 billion years. And our local group of galaxies is a gravitationally bound island in the wider sea. Only when you step out to tens and hundreds of millions of light years, beyond groups and clusters, does the global expansion dominate the story. Light carries the clearest signature of this process. As a photon travels through a universe whose scale is growing, the distance between its wave crests is stretched, its wavelength increases, and its energy decreases. For relatively nearby galaxies, one can describe the effect with the same mathematics as a Doppler shift. But for the deep cosmos, the more faithful description is cosmological redshift. The photon's wavelength is longer because space expanded while it was en route. The same stretching applies to time. When we observe the light curves of distant Type 1a supernovae, their brightening and fading are stretched, time-dilated, by precisely the factor expected from expansion. Flickers in the cores of far-off active galaxies are similarly slowed, not because those systems behave differently, but because the movie arrives on a screen that has been gently widened during the travel of the light. Faintness adds a complementary clue. In an expanding universe, a standard patch of a distant galaxy looks dimmer than in a static one for cooperating reasons. It subtends a smaller angle on the sky. Each photon arrives with less energy because its wavelength has been stretched, and the arrival rate of photons is slowed by the same time dilation that stretches supernova light curves. Together, those effects produce the characteristic surface brightness dimming measured in surveys and predicted by expanding universe models. The cosmic microwave background provides another piece of the puzzle. It is the cooled down afterglow of a time when matter and radiation were coupled. Its near-uniform temperature and tiny ripples are precisely what one expects if the young universe was already expanding and later became transparent, letting relic light stream to us. The present-day expansion rate is summarized by the Hubble constant. Pinning it down precisely has become a central project of cosmology. Local approaches which calibrate distances with Cepheids, the tip of the red giant branch in nearby galaxies, water masers orbiting supermassive black holes, and Type 1a supernovae as standardizable candles, tend to yield a value a bit higher than inferences drawn from early universe probes, such as the microwave background, combined with a cosmological model. This mismatch, known as the Hubble tension, could arise from subtle systematics or hint that our otherwise successful model needs refinement. Either way, the broad conclusion stands firm. The universe is expanding, and the rate at which distant galaxies recede scales with their distance. For much of the 20th century, many expected that expansion would be slowing because gravity pulls on all matter and should gradually decelerate the drift of galaxies. In the late 1990s, however, observations of distant Type 1a supernovae upended that expectation. Those beacons appeared dimmer than a decelerating universe would allow, implying that the expansion is accelerating. A simple explanation is a small, constant energy density associated with space itself, the cosmological constant that exerts negative pressure and speeds the growth of the scale factor. More general possibilities are grouped under the label dark energy, ranging from slowly evolving fields to modifications of gravity on the largest scales. Whichever description ultimately proves correct, the observational consequence is clear. On the biggest scales and over the longest times, galaxies will be carried apart faster and faster. Acceleration has deep implications for what can be observed, even in principle. In a universe like ours, there exists an event horizon. Light emitted today by a source beyond a certain proper distance will never reach us, because the intervening space grows too quickly. As epochs pass, more galaxies slip beyond that horizon. Their light is stretched into wavelengths so long that no conceivable instrument could detect it. Far in the future, inhabitants of the merged remnant of the Milky Way and Andromeda may see only their local collection of bound galaxies, with the wider cosmos erased from view by expansion. We live in that sense in a privileged observational era, with telescopes still able to witness galaxies billions of light years away and to read the afterglow of the early universe. None of this violates relativity's speed limit. A very distant galaxy can recede from us faster than light without anything outrunning a light beam in its immediate neighborhood, because it is space that expands rather than the galaxy moving through space at superluminal speed. Locally, no signal outpaces light. Globally, the yardstick itself changes length and distant points separate accordingly. That distinction resolves a common paradox and emphasizes that cosmic recession is not a conventional velocity, but an evolving geometry. Expansion also sets the background against which cosmic structures formed. In the hot early universe, matter and radiation were tightly coupled. Pressure waves rippled through the plasma and left a faint imprint in the distribution of matter. As the cosmos expanded and cooled, radiation's influence waned, and matter began to fall into the tiny overdensities seeded in the first instance after the Big Bang. Dark matter, interacting primarily through gravity, collapsed first into diffuse halos that merged and grew. Gas followed, cooled, and condensed to form the first stars and galaxies. Expansion moderated the growth of structure on the largest scales by steadily enlarging the playing field, while gravity worked locally to deepen wells. The resulting pattern, dense clusters and filaments separated by vast low-density regions, unfolded within a steadily widening universe rather than in a static arena. Motion in the real cosmos therefore has two ingredients. One is the smooth Hubble flow, the recession from expansion that increases with distance. The other is superimposed local motion, the peculiar velocity induced by nearby mass. A galaxy may be tugged toward a cluster by a few hundred kilometers per second, or drift more easily away from an underdense region. Yet on scales of hundreds of millions of light-years, the Hubble flow dominates and the clean pattern of recession emerges. Our own local group participates in such flows, gently moving toward denser regions while remaining embedded in the overall expansion. If expansion acts everywhere, why does it not pull atoms apart or widen Earth's orbit around the Sun? Because binding forces on those scales, electromagnetism in atoms and molecules, gravity within solar systems and galaxies, are vastly stronger than the feeble kinematic effect of expansion over small distances. Bound systems simply ignore the slowly changing cosmic scale. If you glue a marble to a rubber sheet and stretch the sheet slightly, the marble does not slide, the adhesion wins. In the same way, atoms, planets, and galaxies remain intact, while the very large-scale distances between the islands of matter grow. Independent observations reinforce and cross-check this narrative. The clustering of galaxies shows a preferred scale, a fossil of ancient sound waves in the early plasma that matches expectations for an expanding universe governed by dark matter and dark energy. Weak gravitational lensing, the subtle shearing of background galaxy shapes by intervening mass, maps how matter clumped over time in a way consistent with the measured expansion history. The cosmic microwave background's ripples encode geometry and content at a time only 380,000 years after the Big Bang. When those data are evolved forward, they reproduce the broad features we see in present-day galaxy surveys. Even the time dilation of distant supernova light curves appears exactly as expansion predicts. Each line of evidence is strong. Taken together, they are compelling. Talking clearly about distance in such a universe requires careful language. The separation you would measure if you could freeze cosmic time and lay down rulers everywhere. A proper distance defined at one instant differs from the distance inferred from a photon's long history-laden journey to your telescope. To keep the bookkeeping straight, cosmologists use co-moving coordinates that expand with the universe, so that galaxies at rest with respect to the Hubble flow keep fixed co-moving positions while their proper separations increase. The scale factor, a dimensionless measure of the universe's size relative to some reference epoch, links those descriptions and lets us describe then and now without resorting to equations in a narrative. Measurements also show that the expansion rate has changed character more than once. In the earliest epoch, when radiation dominated the energy budget, the scale factor grew, but with strong deceleration, because the coupled mixture of light and matter behaved like a fluid with significant pressure. Later, when matter came to dominate, deceleration eased, allowing structures to assemble efficiently. Several billion years ago, the sign of the cosmic tug-of-war flipped. Dark energy became the leading component, and net acceleration began. That biography, early deceleration, a long middle age of structure growth, and late time speeding up, emerges independently from supernova, microwave background data, and large-scale structure measurements. On the scale of a human life, none of this is visible as motion across the sky. The nearest galaxy does not drift perceptibly from night to night, and no casual glance reveals space stretching. What we see instead are snapshots at many distances that also represent many times, because light, swift as it is, takes time to cross the expanding stage. Deep surveys assemble those snapshots into a chronology. Nearby galaxies with mature forms, more distant ones in vigorous youth, the most remote appearing as clumpy embryos just taking shape. Each photon carries a timestamp written in its wavelength and energy. When enough are gathered from enough directions, the pattern of expansion emerges, not as a single picture, but as a history. All of this comfortably complements the large-scale structure described elsewhere in this series. The web of clusters, filaments, and broad underdensities describes where matter has gathered. Expansion describes how the separations between gatherings change with time. They are distinct but harmonized aspects of the same cosmos, one revealing spatial pattern, the other temporal evolution. Together, they give us a coherent, testable account of a universe that is both structured and dynamic, a stage that widens while the actors assemble and evolve. If you would like a thought to hold as you settle into rest, take this one. Everything you experience today unfolded in a cosmos where galaxies glide apart at a pace that takes billions of years to matter. You are not required to keep up with that pace. The sky does not hurry, and still everything changes. Now let that calm settle. You do not need to hold the universe together. Gravity and expansion already know their work. Picture distant lights receding on gentle currents, not lost, only following the shape of space. Breathe in and imagine the steadiness of that motion. Breathe out and let your thoughts drift with it, a little farther each time, until the noise of the day softens to something distant and harmless. Above you, the universe widens. Within you, there is room to rest. Chapter 5. The universe has already witnessed countless extinctions and rebirths. The universe is not a static display of stars and galaxies frozen in place. It is a living archive of cycles. Across its history, structures have formed, faded, and formed again in new arrangements. Stars have ignited and gone out. Galaxies have brightened in bursts and fallen quiet. Elements have been fused, scattered, and reassembled. Even planets and biospheres where they arise do not persist unchanged. Extinction and renewal are not exceptions to cosmic order. They are the way the cosmos moves forward, step by step, from simplicity to complexity and back again, in rhythms measured in millions and billions of years. The first great rebirth is the passage from darkness to light. After the hot early universe expanded and cooled enough for electrons to bind to nuclei, the fog of free electrons thinned and relic radiation began to travel freely, the afterglow we see today as the cosmic microwave background. But the gas between nascent structures was neutral and dark, and for hundreds of millions of years there were no stars. Gravity slowly amplified tiny irregularities in density, drawing gas and dark matter together. When the densest pockets finally became hot and tight enough, the first stars, massive metal-free objects, flared to life. They burned furiously and briefly, lived fast, and ended in spectacular explosions, returning the first heavy elements to space. That cycle, birth, brief radiance, explosive death, transformed the universe. Ultraviolet light from those early sources broke apart neutral hydrogen in the intergalactic medium, ionizing it in a patchwork that grew and merged until the dark ages ended. The universe's first extinction was of darkness itself. Its first rebirth was the reappearance of starlight and the emergence of chemistry richer than hydrogen and helium. From that point on, the cosmos refined itself through repetition. The heavy elements made in the hearts of massive stars and in their deaths seeded new generations of stars and the disks of material that become planetary systems. Different stellar deaths left different signatures in the chemical ledger. Core collapse supernovae from short-lived, massive stars produced oxygen, silicon, and many of the elements that build rocks and air. White dwarfs in close binary systems, after slowly stealing matter from a companion, detonated as Type 1a supernova and delivered iron peak elements with a distinctive delay, enriching galaxies long after the first starbursts had faded. Collisions of neutron stars, brought together by the gradual release of orbital energy as gravitational waves, created flashes known as kilonovae and forged some of the heaviest nuclei by rapid neutron capture. A given dust grain can be traced in principle to a particular line in that family history. Carbon condensed in the wind of an aging red giant, iron smelted in a thermonuclear blast, rare heavy elements cooked where two ultradense remnants merged. Much of that dust is later shattered by shocks, its atoms freed to begin again. The same baryons take part in many lives. Entire galaxies follow parallel arcs of ignition and quenching. In the first few billion years after the Big Bang, cold gas flowed efficiently along the threads of the cosmic web into growing halos, fueling rapid star formation. The rate of star birth across the universe climbed to a peak about 10 billion years ago, an epoch astronomers informally call cosmic noon, then declined by an order of magnitude to the present. Some galaxies used up or expelled their gas and fell quiet, their star formation quenched. Others were shut down by their own central engines. As gas fed the supermassive black holes in their cores, the radiation and jets from those active nuclei heated and stirred the surrounding medium, preventing it from cooling and condensing into new stars. Feedback loops like these do not end a galaxy's story. They regulate it. Quenching is not necessarily permanent. A galaxy can accrete fresh gas from its surroundings, merge with a gas-rich neighbor, or pull in material along a filament, and a new wave of star formation can spread across its disk. The light of a spiral arm may therefore be the visible crest of the latest cycle in a long series. Mergers themselves are engines of rebirth and erasure. When two gas-rich galaxies collide, tidal forces torquing their disks can drive cold gas inward, compressing it and igniting a starburst. For a short time, the galaxy pair outshines most of the sky at their distance. Afterward, the same inflow can awaken the central black hole, whose energy in turn can blow out or heat the remaining gas, slowing future star formation. The stellar orbits, once ordered in neat disks, are scrambled into a puffier, rounder configuration, and the morphology shifts toward an elliptical or lenticular shape. In these events, nothing is perfectly lost. Stars rarely collide, and most survive to orbit in new patterns. The gas that is expelled may cool later and be reaccreted. Satellite galaxies that are shredded become part of a halo of faint light, their stars still circling as a diffuse memory of histories combined. Not every transformation is driven by violence. In the quiet outskirts of galaxies, star formation proceeds slowly as cool gas clouds turn gradually into stars. Those stars return gas to space through winds and gentle mass loss as they age, keeping an internal cycle alive. Within disks, spiral patterns and bars redistribute angular momentum and gas, bringing fuel toward the center to spark nuclear rings of new stars or, over longer stretches, to feed the central black hole in sips rather than gulps. The overall look of a galaxy can change in these ways without a single headline event. Enough small edits produce a new draft. The medium between galaxies and clusters plays its part in endings and renewals. When a galaxy plows through the hot, thin plasma that fills a cluster, the pressure it feels can strip cold gas from its disk, quenching star formation and leaving a trail of material that glows briefly where new stars ignite in compressed knots. Galaxies passing near others suffer repeated gravitational tugs that heat and thicken their stellar distributions, making them more spheroidal and less able to sustain organized waves of star formation. Those same interactions unbind stars, which become part of the intracluster light, a ghostly glow that lights the spaces between galaxies with the combined output of stars long since removed from any single parent. The cluster as a whole experiences cyclic regulation too. Its hot atmosphere radiates, which would lead to cooling flows and central starbursts, but jets and bubbles from the central black hole inject energy that arrests the runaway condensation. The result is not an end to star formation, but a gentle balance, with small flows and intermittent flickers around a long average. Planetary systems condense, evolve, and sometimes erase themselves in miniature versions of these cycles. Young stars are surrounded by disks of gas and dust that dissipate in a few million years, leaving behind planets, asteroids, and comets. The histories of those systems are not smooth. Gravitational interactions can drive planets inward or outward, reorganize orbits, and even eject worlds entirely. Collisions between protoplanets produce debris disks, and eventually, larger bodies. The scars of that epoch are visible on the faces of many worlds. At later times, stars shed mass, expand, and change their radiation in ways that alter or end planetary habitability. Some close-in planets are engulfed when their stars swell. Others are stripped of their atmospheres by intense ultraviolet and X-ray light. Each of these is a kind of extinction, not an end to matter, but a termination of familiar conditions, followed by a reconfiguration of what remains. Even at the level of a single star, erasure and renewal leave clear imprints. When a massive star dies in a core collapse supernova, its shock front can compress nearby gas clouds and seed the next generation of stars. A stellar death can be the midwife to stellar birth. White dwarfs secreting from companions can tip into thermonuclear explosions that carve cavities in the interstellar medium, inject iron and nickel, and send shock waves rippling outward, accelerating cosmic rays that later strike clouds and surfaces far away. In the gentle winds of aging giants, dust grains condense and flow out, later to be ground down by shocks and mixed into the gas that will collapse into new systems. The interstellar medium is not a single reservoir, but a circulatory system of inflows, outflows, cooling filaments, hot chimneys, and long-range fountains that carry enriched gas out of disks and then rain it back down after it cools. Across cosmological time, the balance among these processes changes. In the early universe, gas supply was abundant and the pace of star formation high. As galaxies converted gas into stars and expelled the rest with winds and jets, the number of fresh, inflowing streams waned, and the average galaxy's factory slowed. The quenching of star formation gathered momentum in massive galaxies while smaller systems continued to flicker. In the present epoch, new stars still form, but the cosmic rate is far below its ancient peak. The future, on long timescales, points toward a quieter sky as fuel is locked into remnants or ejected beyond easy recall. And even then, cycles will continue at lower amplitude. Dwarf galaxies will merge or be tidally shredded. Occasional gas clouds will fall in and trigger local starbursts. Compact remnants will collide and light the darkness in brief, bright transients. The evidence for this picture is broad and consistent. Deep surveys that slice the sky by distance reveal that the colors and spectral features of galaxies shift in step with the expected rise and fall of star formation over time. X-ray and radio maps show shock fronts, relics, and bubbles that record the on-off duty cycles of black holes and the turbulence they drive. Spectroscopy of stars within the Milky Way traces distinct chemical families, alpha element-enhanced populations that formed quickly and iron-rich populations that formed later, reflecting the different delay times of the explosions that enriched them. The faint halos around galaxies are laced with streams whose motions and metallicities tell of past accretion events. In the intergalactic medium, absorption lines against the spectra of background quasars reveal the flow of enriched gas far from any galaxy, a signature of outflows and recycling on scales larger than any single disk. Cycles can even be watched in real time, albeit at the pace of decades rather than eons. A star ripped apart by a supermassive black hole flares and fades as its debris streams in. A supernova lights a galaxy and then declines, leaving behind a remnant that expands and cools while its shock crashes into older ejecta and ambient gas. A quasar dims as its supply runs out and its jets falter, leaving cavities in cluster gas that rise and break, mixing heat through the atmosphere. In each case, what looks like an ending is also an adjustment, one phase giving way to another in a larger sequence. There is a small existential thought to keep from all of this. The atoms that make you were part of many endings before they arrived here, and the patterns they form in you are temporary arrangements in a universe that never stops editing itself. That is not a diminishment. It is a reminder that renewal is built in. As the day closes, let that rhythm ease your breathing. Picture a nebula brightening where a shock front passes, then fading as the stars it birthed drift on. Imagine a galaxy that burns hot for a time and then rests, not as a failure, but as a phase. Your thoughts can do the same. Let the sped ones fall away like old gas and allow quiet to be the space where something gentler can form. The sky above you is full of cycles far too slow to worry you. In their patience, there is room for sleep. Chapter 6. Time runs differently on cosmic scales. Time is not a single rhythm that ticks the same everywhere. In daily life, we can act as if it were. The minutes on a kitchen timer, the hours written by the sun across a window, the steady pulse of an atomic transition. Step outward, and that simplicity dissolves. Motion and gravity reshape the rate at which clocks run. Distance folds history into every direction you look. Processes that take microseconds and processes that take billions of years coexist in the same universe, and the meaning of now depends on where you stand and how you move. To describe the cosmos, we have to let go of a single universal clock and accept that time is woven together with space and with matter into a fabric that flexes. Relativity made this plain. It replaced the comfortable idea of an absolute universal time with space-time, a four-dimensional stage in which intervals of space and time mix. If two observers move swiftly relative to one another, each will find the other's clock running slow and the other's ruler shortened. Neither is wrong, because time and space are not separate invariants but aspects of the same geometry. Gravity deepens the effect. Where mass curves space-time, time passes more slowly. A clock set deeper in a gravitational potential runs at a different rate from one set higher up. The rule is not an opinion. It is built into the way light travels and particles move. Near compact objects, the same rules play out on a dramatic scale. A neutron star packs more mass than the sun into a sphere the size of a city. A visitor skimming that surface would find local processes, atomic vibrations, heartbeat-fast pulsar spins, running on a clock that, when compared to a distant observer's, is slowed by the star's intense gravity. Near a black hole, the effect grows stronger still. As light climbs out from close to an event horizon, it is redshifted, its wavelength stretched and its clock slowed. From far away, the last moments of infalling material look drawn out and dim. For the matter itself, nothing exotic interrupts the local flow of proper time as it crosses the horizon. Both descriptions are correct within their frames. Time is not broken, it is local. Motion alone produces similar changes. The faster an object travels relative to you, the less proper time elapses for it between two events you both can mark. This is not a mechanical wear on the clock, but a geometric fact about paths through space-time. Nature supplies laboratories for this truth. Millisecond pulsars, neutron stars spinning hundreds of times per second, send beams sweeping across Earth with astonishing regularity. In binary systems, as a pulsar moves toward us and then away along its orbit, the arrival times of the pulses shift in a way that records both motion and gravity's influence on the flowing seconds. Over years, the orbit itself shrinks as the system radiates energy in gravitational waves, and the changing clockwork is measured in the steady drift of pulse times. Cosmology adds yet another kind of stretching. The universe has been expanding for 13.8 billion years, and that expansion lengthens light in flight. A photon leaving a galaxy, when the universe was half its current size, will arrive with its wavelength doubled. The same factor stretches every time signature encoded in that light. A supernova that brightened and faded over 30 days in its own rest frame will take proportionally longer when observed at high redshift. Distant active galactic nuclei flicker on elongated schedules compared to similar objects nearby. Time dilation is written into the sky. Distance also turns direction into history. Light is fast, but the universe is large. The Andromeda Galaxy is seen as it was more than 2 million years ago. The Virgo cluster as it was tens of millions of years ago. The most remote galaxies as they were when stars were young and heavy elements rare. No telescope can show the universe as it is now everywhere at once, because now is a local slice through space-time. Astronomy is an archive of delayed messages. Each photon that reaches a mirror carries the date of its departure encoded in its energy, its spectrum, and the changes it has suffered en route. To keep the chronology straight, astronomers use several complementary notions of time. Proper time is what a single clock measures along its path, the lived time of an object or observer. Coordinate time is the bookkeeping used to compare separated events within a chosen frame. For cosmology, the natural frame is one in which the average sea of galaxies is at rest, and the expansion looks uniform. The time that flows along those slices is called cosmic time. When we say the universe was about 1 billion years old, when the fog of intergalactic gas was reionized by the first generations of luminous sources, or that it was about 380,000 years old when atoms first formed and light began to travel freely, we are speaking in terms of cosmic time. Different clocks allow us to cross-check the story. White dwarfs, the embers of ordinary stars, cool in a predictable way. Counting white dwarfs at different temperatures in a star cluster provides a clock for the cluster's age. The ratios of long-lived radioactive isotopes in old stars and in meteorites give another chronometer that complements stellar evolution models. The seismic ringing of stars, read from minute brightness variations, reveals their internal structure and age. Pulsars, with their metronomic ticks, time the dynamics of their own systems and trace the ripples of passing gravitational waves. Each method has its limits and uncertainties. Together they weave a consistent timeline. Not all differences in time are about clocks disagreeing. Many are about processes that run on tempos unfamiliar to our senses. A cold, dense molecular cloud can take 10 or 20 million years to transform a small part of itself into stars. The spiral pattern drifting through a galactic disk can take hundreds of millions of years to complete a circuit. The slow drag called dynamical friction, which robs a satellite galaxy of orbital energy and draws it inward toward a larger companion, unfolds over billions of years. In clusters, shock waves crawl through the hot atmosphere over gigayears, and the gentle feedback between a central black hole and the surrounding gas cycles on 100-million-year loops, preventing runaway cooling without extinguishing it entirely. These are the tempos of assembly and regulation on the largest stages. At the other extreme lie transients. A magnetar, a neutron star with an immense magnetic field, can crack its crust and produce a burst of gamma rays in a fraction of a second. A fast radio burst may last only a few milliseconds, yet release as much energy as the sun emits in days. The shock that triggers a supernova crosses a massive star in minutes, even if the optical light from the explosion takes weeks to rise and fade. Gravitational waves from a pair of merging neutron stars sweep upward in frequency and amplitude during their final seconds. The light from the associated kilonova unfolds over days. These brief events are not exempt from cosmic timing. At high redshift, they too are stretched by expansion, their flashes lengthened into gentler arcs. Gravity has a way of giving time two faces. As gas falls into the deep potential well of a black hole, its internal clock slows compared to a distant one. Close to the horizon, the light it emits is so redshifted that an outside observer receives a slow, faint stream. Yet for the infalling matter, proper time to cross the horizon is finite and uneventful. Both descriptions are true within their frames. A similar duality appears in lensed systems. When a massive galaxy lies between us and a distant quasar, its gravity splits and bends the quasar's light into multiple images that take different paths to reach us. If the quasar brightens and dims, the variations appear at different times in the separate images. Those time delays encode both geometry and gravity. By measuring them, astronomers can infer distances and the expansion rate, time used as a ruler, space used as a clock. Translation among timescales is the quiet craft of modern astronomy. Observers measure redshifts, fluxes, and variability. They convert those into look-back times and distances using models tested against many independent probes. They count standard candles and standard rulers, fit the history of expansion, and turn that into a clock that can be used elsewhere. To date, when the first stars formed in a given region, to estimate how long a galaxy has been quiescent, to judge whether there has been time for rocky planets to assemble and cool around a particular star. The coherence that emerges, the way different clocks agree when adjusted for motion and gravity, gives confidence that the narrative is not an artifact of any one method. Human lives are short compared to many of these tempos, but we are not blind to change. Over decades, we can see a supernova flare where no star was visible before, watch its light curve stretch if it lies at high redshift, and trace the expanding remnant as it plows into surrounding gas. We can time a pulsar so precisely that we notice its orbit precess and its period drift as gravitational waves carry energy away. We can watch a quasar brighten and fade, and measure the echo of that variability in the multiple images created by a gravitational lens. We can detect the passage of gravitational waves through a galaxy-scale array of millisecond pulsars by the way their ticks slip in and out of sync. Time, even on cosmic scales, leaves marks within a single human generation. All of this returns us to a simple truth. Time is local and plural. Your heartbeat, a pulsar's spin, a white dwarf's cooling, and the slow widening of the universe are all clocks, and they do not always agree. Yet their disagreements are not chaos. They follow rules we can write and test, and their differences can be translated. That is why the same cosmos can contain nanosecond flashes and billion-year drifts and still be one connected story. For tonight, let that variety of tempos soften your own. Imagine time becoming spacious, as if the day's tight minutes were being gently unknotted. Picture distant signals arriving after journeys so long that hurry has no meaning. Breathe in and let your thoughts lengthen like waves red-shifted by a calm and ancient expansion. Breathe out and let the urgency go. Above you, the universe keeps many clocks, none in conflict. Within you, there is room to rest beside them. Chapter 7. The universe moves in rhythms too vast to notice. If you listen closely enough, the universe is full of beats. Some are quick and crisp, stellar pulses you can graph over nights or weeks. Others are so slow that no single lifetime can hear them finish a bar. The turn of a galaxy around its center, the gentle slosh of cluster gas after a merger, the rise and fall of star formation across billions of years. None of these rhythms is a metronome for everything. They are local patterns, nested and overlapping, carried by gravity, pressure, magnetic fields, and motion. Together they form a quiet music too spacious for urgency, yet precise enough to measure. Start with orbits, because orbital motion is the most universal rhythm we know. Planets circle stars, moons circle planets, and in the same way stars circle the centers of galaxies. Our sun moves around the Milky Way once every roughly 250 million years, a galactic year that has ticked perhaps 20 times since the sun first formed. That motion is not perfectly circular. Stars bob up and down through the galaxy's thin disk on vertical oscillations that take tens of millions of years, and they drift inward and outward slightly in epicycles, small radial beats imposed on the longer orbital sweep. These combined motions are choreographed by the galaxy's gravity, mostly dark matter, some stars, some gas, producing wide, slow rhythms that govern how often a star like the sun encounters spiral arms or passes through denser lanes of gas. Spiral patterns themselves are a kind of rhythm. They are not rigid pinwheels glued to the disk, but density waves, regions where stars and gas briefly crowd together, linger, and then move on. The pattern rotates with its own speed, the core-rotation rate, while individual stars orbit a bit faster inside that radius and a bit slower outside. As gas enters a spiral arm, it is compressed, cools, and forms stars. As it exits, new stars drift into the arm's wake. The result, seen edge-on in infrared and radio images, looks like lanes and feathers, but it is also a beat, an alternation of higher and lower density sweeping through the disk over hundreds of millions of years. Galaxies often carry bars, elongated stellar structures that rotate as a unit and set up resonances in the surrounding disk. Near the bar's ends, gas can pile into rings at specific resonant radii, where orbital frequencies match simple ratios to the bar's pattern speed. Over time, bars may buckle, thickening into a boxy or peanut-shaped bulge before settling again, a long, slow cycle driven by angular momentum exchange with the dark matter halo and with the disk. Pattern speeds can gradually decline as the bar transfers angular momentum, changing the locations of resonances and subtly shifting the spatial rhythm of star birth. On larger scales, groups and clusters of galaxies experience rhythms of another sort: sloshing, ringing, and relaxation. When a small group falls into a more massive cluster, its gravity and motion set the cluster's hot, X-ray bright atmosphere into oscillation. Contact surfaces, called cold fronts, arc like ripples on a pond, wrapping and re-wrapping around the cluster's center as gas with different histories slides and swirls without mixing. These features persist for billions of years, recording a long echo of the original disturbance. In radio frequencies, diffuse halos and edge-brightened relics light up along shock fronts produced by the same mergers, fade as electrons lose energy, and can be re-energized when the atmosphere is disturbed again. A cycle of acceleration and cooling that plays out over 100 million year periods. Even the inflow and outflow of gas in galaxies carries a cadence. Star formation and black hole activity are not truly steady. They flicker. Cold gas trickles inward from filaments, collects in clouds, and forms stars. Supernovae and stellar winds then stir and heat the surrounding medium, driving some gas outward in fountains. Over tens to hundreds of millions of years, a fraction of that gas cools at larger radii and rains back onto the disk, ready for another round of collapse. The central supermassive black hole follows its own duty cycle. When fresh fuel reaches the nucleus, the black hole brightens as a quasar or Seyfert galaxy for tens of thousands to millions of years. When the supply dwindles, the light and jets fade. In some systems, clouds of gas fluoresce with the memory of a recent bright phase, light echoes that reveal a rhythm too slow to catch live, but not too slow to trace. There are rhythms so ancient they have frozen into fossils. Before atoms existed, the early universe was a hot plasma where pressure and gravity set up sound waves. Those waves left ripples in temperature and density that we still see in the cosmic microwave background. Later, as the universe cooled and atoms formed, the ripples stopped traveling. Their preferred scale, about a few 100 million light-years in today's units, remains imprinted as a subtle excess of galaxy pairs at that separation. This feature, the baryon acoustic oscillation, is a relic beat, a fossilized bar in the score that lets astronomers keep time when they measure how expansion has changed. We have met this ruler elsewhere, but here the point is its musicality. The universe once rang like a bell, and the bell's tone is still audible in its structure. Stars themselves are intricate instruments. Cepheids and RR Lyrae inflate and deflate with periods set by the interplay between gravity and opacity in their outer layers, turning on and off a valve that regulates the flow of radiation. Their regular pulses, stable over years or decades, make them reliable distance markers. Solar-like stars host subtler rhythms. Sound waves bounce within their interiors and make their surfaces quiver. By reading those tiny brightness variations, a technique called astroseismology, astronomers infer a star's internal structure and age as one might characterize a violin by listening to its harmonics. Red giants exhibit mixed modes that probe both outer envelopes and deep cores, revealing rotational shears and evolutionary stages. These are short rhythms by cosmic standards, but they are connected to slower cycles. A star's oscillations change as it ages, and ensembles of stars across a galaxy encode the long demographic beat of stellar birth and death. Magnetism adds more tempos. The sun's magnetic field flips polarity on an 11-year cycle, modulating sunspots, flares, and the speed of the solar wind. Other stars exhibit similar cycles, some slower, some faster, tied to rotation and convection. On galactic scales, large-scale dynamos, driven by differential rotation and turbulence, can organize magnetic fields over tens of thousands of light-years, potentially reversing over hundreds of millions of years. While hard to time precisely, these slow magnetic cycles shape where cosmic rays travel, how gas collapses, and how star-forming clouds fragment, quiet rhythms that leave structural consequences. There are gravitational rhythms so deep and slow that only patient timing can hear them. When two supermassive black holes orbit one another after their host galaxies merge, they take millions of years to spiral together. The ripples they send into space-time have wavelengths measured in light years and frequencies measured in billionths of a hertz. We cannot hear that with a single detector, but a galaxy-sized array of millisecond pulsars, ultra-stable neutron star clocks, can. As gravitational waves pass between us and those pulsars, the ticks arrive early or late by tiny amounts. Averaged across many pulsars, those advances and delays reveal a common, correlated background, a low celestial hum from countless black hole binaries across the universe. It is the definition of a vast rhythm, cycles measured in decades of observation to infer sources that take eons to complete an orbit. Planetary systems carry nested rhythms that, while closer to home, speak to the universality of gravitational dance. Axial precession slowly reorients a planet's spin axis. Orbital eccentricity and tilt vary on tens of thousands to 100,000-year cycles. Mutual tugs among planets exchange angular momentum in secular beats that take millions of years to play out. On Earth, those Milankovitch cycles modulate climate by changing the distribution of sunlight across seasons and latitudes. On other worlds, similar cycles alter ice, atmospheres, and winds. Though local, these rhythms are honest expressions of the same mechanics that scale upward to galaxies and clusters. Gravity does not only bind, it also composes. After mergers, galaxies often ring. Tidal encounters set disks vibrating in bending and breathing modes, up-down ripples that sweep across the stellar plane. Streams torn from dwarf galaxies wrap around their hosts and exhibit regularly spaced overdensities, feathering from epicyclic motion as stars released together drift and reconverge. In the Milky Way, surveys have found vertical waves and phase space spirals in local stellar velocities, signatures of a perturbation in the recent past, likely a small satellite's last pass. These are audible rhythms on the human timescale only because we can map many stars at once and reconstruct the beat from their current phases. The oscillations themselves spans to hundreds of millions of years per cycle. Even the seemingly chaotic flows of gas follow cycles with characteristic times. Giant molecular clouds, the nurseries of stars, assemble, form clusters, and disperse in 10 to 30 million years. Feedback from the newborns, ionizing radiation, winds, and supernova, shreds their parent clouds on roughly the same schedule, and then the interstellar medium cools, recombines, and begins again. On galactic scales, this creates a self-regulated pattern in which the rate of star formation hovers near a balance set by gravity, turbulence, and pressure. The pattern is not perfectly periodic, but it is rhythmic, bursts and lulls, each influencing the next. Clusters, too, show feedback cycles. In cool core clusters, gas in the center ought to cool rapidly and collapse, yet starbursts there are modest. The reason is a feedback loop. As gas tries to cool, it feeds the central black hole. The black hole responds with jets that inflate bubbles and gently heat the surrounding plasma. The heating throttles the cooling, which reduces the fuel, which dims the jets, allowing cooling to resume. Over hundreds of millions of years, this back and forth keeps the core from either runaway condensation or permanent quenching. X-ray images reveal cavities and weak shocks. Radio maps show fossil lobes. Together, they sketch a heartbeat. Some rhythms are made visible by light's travel time. In strongly lensed systems, a distant quasar's variability appears in multiple images at different delays because each photon path is a different length through curved spacetime. By measuring those delays, astronomers infer distances and expansion history. The quasar's own flicker, often chaotic, becomes a tracer of geometry, an irregular beat repurposed as a ruler. On kiloparsec scales, ionization echoes, gas clouds lit by a nucleus that has since dimmed. Let us time the recent on phases of a galaxy's core. On megaparsec scales, the alignment of galaxies and clusters with nearby filaments reveals anisotropic infall that persisted over long intervals, leaving behind harmonic structure in positions and spins. Because the rhythms are so slow, they can be comforting. The sun will pass in and out of spiral arms on timescales that make continents look like brief weather. The Milky Way's bar will turn slowly while cold gas gathers and releases, while clusters ring and settle. Supermassive black holes will continue their long courtships, broadcasting a gravitational murmur that we can only discern by comparing many clocks over many years. Nothing in this music demands haste from us. Nothing in it is improved by worry. So as you set the day down, imagine those rhythms spreading outward. Picture a disk of stars turning so slowly that its rotation becomes a soft assurance rather than a countdown. Picture a cluster's gas ringing once after a distant collision, then resting. Picture a background of gravitational waves humming invisibly, felt only in the way a few stellar clocks slip their ticks by a breath. Breathe with that space. Let your thoughts follow the longest arcs and fade into the quiet between them. The night does not hurry, neither must you. Chapter 8. The far future belongs to quiet darkness. Look far enough ahead, and the universe you know thins into something spare and slow. The bright epoch of stars, galaxies, and colorful nebulae is not the end of the story, but a vivid chapter in a much longer book. The forces and ingredients that sculpted today's cosmos, gravity, expansion, radiation, and matter in its familiar forms. Keep working on horizons measured not in millennia, but in powers of 10 that stretch beyond ordinary language. In that future, light does not vanish all at once, it ebbs. Structure does not collapse, it loosens. The universe moves toward states in which energy differences flatten out and the conditions for sustained complex activity become rare. What remains is not drama, but duration, a long settling in which almost everything that can shine has already done so. The path to quiet begins long before the last star. It begins with a steady decline in the raw material for star formation. In the early universe, cold gas streamed along filaments into dark matter halos, and the rate of star birth surged to a peak roughly 10 billion years ago. Since then, that rate has fallen, on average, as gas was locked into stars or heated and expelled by stellar winds and black hole jets. Some gas is recycled by galactic fountains and returned, but not in the torrents of earlier times. The decline is not uniform. Galaxies continue to flicker with local bursts when mergers or inflows supply fuel. Yet the trend is clear. The reservoir depletes, and with it the cosmic capacity to kindle new suns. In the nearer future, the most enduring stars, red dwarfs with thrifty fusion, will come to dominate the light as their larger, faster-burning cousins fade from the scene. Gravity, meanwhile, keeps tightening bonds where it can. The Milky Way and Andromeda will merge within a few billion years, their stars mostly passing without collision, while their dark matter halos and gas interpenetrate. The local group will relax into a single, massive elliptical-like remnant surrounded by a diffuse halo of stars, streams, and globular clusters. An island of matter bound by gravity's patience. Beyond that island, cosmic expansion continues to widen separations. Because the universe's expansion is accelerating, Structures not already gravitationally bound to us will recede beyond a horizon from which their light can never arrive. Over tens to hundreds of billions of years, that horizon erases the wider web from view. What remains observable is the island itself. First many islands, then a few, and eventually just the local remnant, adrift in a deepening dark. Within this island, star formation dwindles, but does not cease abruptly. Gas heated by mergers and feedback will cool only reluctantly, and new stars will be made from leftovers. The slow collapse of dense clouds, the occasional accretion of a gas-rich dwarf, or the tidal stirring of material in the remnant's outskirts. The typical products will be long-lived, low-mass stars whose supplies last trillions of years. Even as the general background dims, red dwarfs quietly fuse hydrogen into helium in their small cores, wasting little. The main sequence lifetimes of such stars can exceed the present age of the universe by orders of magnitude. So for an immense stretch of future time, the galaxy, whatever its merged form, will be lit by countless faint embers rather than a few grand beacons. The slow evolution of those embers is itself part of the transition toward quiet. Theory suggests that as red dwarfs age, internal changes can drive them to higher temperatures and luminosities near the end of their lives, a late brightening before they finally exhaust their fuel. After that, they leave no dramatic supernovae. They end as white dwarfs, dense, degenerate cores of carbon and oxygen, or, for the very lowest masses, helium, gravitationally supported not by heat, but by quantum pressure. White dwarfs shed their residual warmth over enormous timescales. As they cool, their interiors crystallize, a phase change on a stellar scale, releasing latent heat and briefly slowing the fade. Eventually, after spans so long we can only gesture at them, the remnants cool below any starlight-driven reference, becoming black dwarfs, dark, cold relics with the mass of a star and the size of a planet. Not all stellar endings are quiet. Massive stars, while they still exist in the nearer future, end in core collapse supernovae that leave neutron stars and black holes. Those remnants outlast everything luminous. Neutron stars, city-sized spheres of neutrons, cool rapidly at first, then more slowly, their magnetic fields decaying and their beacons of radio emission dimming. Black holes, from a few solar masses to supermassive giants at galactic centers, persist as the deepest wells in the gravitational landscape. In the merged remnant of a galaxy group, stars and stellar remnants scatter off one another over long times, a process called two-body relaxation. Some are nudged onto orbits that carry them into the central black hole. Others are ejected into intergalactic space. The distribution changes gradually, but its long-term trend is toward depopulation of the center by sacrificial infall and depopulation of the outskirts by slow escape, a drifting apart within the bound island. As the luminous era fades, the backgrounds fade with it. The cosmic microwave background, the residual glow from when the universe first became transparent, cools as space expands, its temperature falling inversely with the scale factor. It was once thousands of Kelvin. It is now a few degrees above absolute zero. It will asymptotically approach colder and colder values. The integrated starlight of the cosmos, already vastly dim at the largest distances, will be redshifted into wavelengths so long that it washes into the radio quasi-silence. Neutrino backgrounds from the early universe persist, ghostly and almost non-interacting, but they too grow colder. Locally, the diffuse X-ray plasma in cluster-like remnants sheds energy and cools, though feedback and dark energy's accelerated expansion limit the supply of fresh matter to replace what was lost to stars long ago. The overall direction is toward thermal uniformity. the rough equalizing of temperatures that removes the free energy gradients needed to do sustained work. There are nevertheless late sparks and murmurs. Compact remnants will continue to collide on rare occasions. A stray neutron star driven into merger by encounters, a black hole capturing and tearing apart a white dwarf, an evaporating substellar object stumbling too near the central well. Each event would be a brief signal in the darkness, an electromagnetic flare, a burst of neutrinos, a ripple of gravitational waves, followed by longer quiet. The cadence, already sparse, thins further as orbits widen, reservoirs deplete, and the island isolates itself more completely from external supply. The age of frequent punctuation gives way to a sparse semicolon every incomprehensible interval. If protons are unstable, something experiments have not yet shown, then on timescales many orders of magnitude longer than stellar lives, the very fabric of ordinary matter would change. Baryons would decay into lighter particles, slowly reducing planets, white dwarfs, and even the material in neutron star crusts to a bath of radiation and leptons. Current limits push any such lifetimes far beyond 10 or 34 years, and they may be much longer or infinite. If the proton does not decay, then degenerate remnants and rocky matter can persist. The far future hinges on this uncertainty only beyond spans that dwarf already unimaginable eras. In either case, the salient feature of the late universe remains. Complex, low-entropy structures become fewer, colder, and more isolated. Black holes sit at the end of almost every path. In a universe whose large-scale expansion is accelerating, there is a horizon even in perfect emptiness, and horizons are not silent. They have a temperature, tiny but non-zero, associated with quantum fields in curved spacetime. Black holes possess their own faint temperature, inversely proportional to mass, and therefore radiate extremely slowly. For a solar mass black hole, that thermal glow is unimaginably weak, swamped for eons by higher background temperatures. But the background falls. In the remote future, once the ambient radiation cools below a given hole's effective temperature, evaporation wins. The hole loses mass, warms, and loses mass faster. Stellar mass black holes would take many, many orders of magnitude longer than the current age of the universe to evaporate. Supermassive black holes would persist longer still. Each ends with a final brief crescendo, converting the last fraction of its mass into a burst of high-energy particles and radiation. That, too, is a punctuation, isolated, rare, and followed by longer quiet. What follows those endings is sometimes called the dark era. With the last long-lived stars extinguished, with white dwarfs cooled and black dwarfs dormant, with neutron stars inert and black holes finally dispersed into their radiation, the universe contains no persistent engines of light. It is not empty in any absolute sense. It is filled with low-energy photons, neutrinos, and, depending on the fate of protons, a sprinkling of electrons and positrons or their decay products. Quantum fluctuations can still produce transient excitations. Rare encounters among the coldest relics could happen, but they would not lead to sustained complexity. The cardinal fact is that entropy has approached a maximum within what the universe allows. In the language of thermodynamics, there are no longer gradients to exploit. Dark energy shapes not just isolation, but the texture of this endpoint. If the acceleration continues as a simple cosmological constant, the universe approaches a de Sitter-like state with a fixed horizon and a tiny constant temperature associated with that horizon. That temperature is so low that it matters only as a bookkeeping entry, an ambient bath colder than any astrophysical process we can name today. If instead, the energy density that drives acceleration changes over time, then the detailed path to the endpoint would differ, but the direction would remain similar, toward dilution, isolation, and faintness. The far future's character does not depend sensitively on the fine print. It depends on the robust trends of dwindling fuel, persistent expansion, and the neutrality of thermodynamics. There are hypotheticals at the edges. Some calculations suggest that under extraordinary pressures and timescales, quantum tunneling might ignite reactions in the heart of the coldest remnants, leading to rare outbursts even in a universe without ordinary fuel. Other speculations imagine vacuum decay, an abrupt change in the ground state of quantum fields that would rewrite the laws governing particles and forces. These possibilities sit far beyond current evidence. They mark the limits of projection, not a reliable forecast. The safest picture remains the simplest. After the long, bright era fades, the universe becomes an archive of relics and a bath of almost featureless radiation. For observers who might exist along the way, the informational horizon closes before the light does. Long before the last red dwarf exhausts its fuel, the accelerating expansion guarantees that most galaxies slip beyond visibility. The empirical clues that allowed us to reconstruct the Big Bang, the cooling microwave background, the fossil scale of early sound waves, the recession of distant galaxies, grow too faint to detect. The island cannot see the sea in which it floats. Future astronomers, if there are any, will reconstruct a different story, a lone-bound system in a long-lived equilibrium, with little evidence of a broader stage. The irony is gentle but sharp. We live in a cosmological Middle Age that is uniquely rich in clues. The quiet darkness does not so much erase truths as make them inaccessible to finite beings within it. None of this is tragic in the language of physics. It is the unfolding of initial conditions under universal laws, the way energy and matter explore their possibilities. The bright era of stars is not diminished by having an end. It is defined by contrasts that only change can supply. The same atoms that cooled from the early fireball rose into clouds, kindled as stars, forged heavier elements, assembled into planets, and at least once, in at least one corner, organized into a creature that could trace its history. Those atoms will go on to other fates, quiet ones. The universe will not remember in any narrative sense, but its relics will embody the path it took, and for tonight, let that noticing be enough. You do not need to keep vigil over distant futures or hold the cosmos in mind. The universe will take care of its own settling. You can practice a smaller version of that quiet. Imagine the lights of the day receding as gently as galaxies slip beyond a horizon. Picture the mind's activity cooling like a white dwarf, its heat given back to the surrounding calm. Breathe in slowly and feel the edges soften. Breathe out and let the last bright thoughts fade into a comfortable dark. Above you, the long exhale has already begun. Within you, there is room to rest beside it. Chapter 9. Beyond the observable horizon, the universe continues. Stand outside on a clear night and you're already looking into the past. Starlight takes time to travel, and the farther a source lies, the older the message it carries. Push this idea to its limit, and you reach a boundary that is not a wall, but a limit set by time itself, the observable universe. It is the portion of the cosmos from which light, moving at a finite speed through an expanding space, has had time to reach us since the hot beginning. That boundary is real in the sense that it marks the edge of information, not the edge of existence. There is no reason to think the universe ends there. All our best models indicate that beyond the surface we can see, the same cosmos continues. Stars and galaxies, clusters and filaments, voids and flows, extending into regions forever out of contact with us. The horizon is an epistemic frontier, not a physical shell. To see why a horizon exists, remember two simple facts that have guided earlier chapters. Light is fast but not instantaneous, and space itself is stretching. If you draw the history of the cosmos as a diagram of light cones, paths that light can follow in space-time, your own world line, the continuous thread of your existence, sits at the tip of a widening cone of visibility. The surface of that cone at any given moment defines how far into space and time you can see. Objects farther away are not hidden behind a curtain. They are simply too distant in space-time for their signals to have arrived yet. Add expansion and the subtlety grows. While a photon was crossing the gulf itself grew. So the present-day distance to the matter that emitted that photon can be far larger than the distance light covered at the time of emission. This is why, even though the universe has been expanding for about 13.8 billion years, the radius of the observable region today is several times larger than 13.8 billion light-years. We see a sphere of ancient light whose present-day sources lie tens of billions of light-years away. Beyond that sphere, the universe quite plausibly looks much the same, but its light has not, and in many cases, will never reach us. The concept of a horizon comes in more than one form. The particle horizon is the boundary of what has been observable since the beginning, the maximum distance from which a signal could have arrived by now. It grows with time because each year adds a new layer of space-time from which light has finally had time to reach us. In a universe that is expanding and also accelerating, as ours is, there is another horizon with a different meaning, an event horizon. It marks the distance beyond which events happening today can never influence us in the future, no matter how long we wait, because the expansion will carry those regions away too quickly for their light to ever catch up. The two horizons do not coincide. We can currently see galaxies whose present-day positions already lie beyond our event horizon. We are receiving their ancient light, but nothing they emit now will ever arrive. This layering of boundaries is a natural consequence of cosmic kinematics, not a paradox. The light that reaches us left those galaxies when the universe was smaller and our mutual separation was within the reach of a photon. The universe grew while that photon was en route, and by the time it arrived, the source had been carried beyond the sphere of future influence. What then lies outside the observable domain? The most conservative answer, the one least burdened by speculative assumptions, is more of the same. Observations of the cosmic microwave background show the geometry of space to be very nearly flat on large scales, with any curvature, if present at all, too small to measure with current instruments. A nearly flat space can be finite or infinite depending on its global topology, but a flat space that is finite would have to fold back on itself in ways that leave repeated patterns on the sky. Matched circles in the microwave background where light has wrapped around the universe more than once. Astronomers have searched for such patterns and have not found them. That null result does not prove space is infinite, but it does push any global repetitions far beyond what we can see. Coupled with the observed uniformity of the microwave background and the large-scale distribution of galaxies, the inference is that our observable patch is embedded in a much larger, likely vast region with similar statistical properties. The same physical laws, the same mixture of matter and radiation and dark energy, the same web-like arrangement of structures on the largest scales. Inflationary theory adds support to this picture. It proposes that in the first tiny fraction of a second, The universe underwent a brief, violent burst of accelerated expansion that smoothed and flattened space while stretching microscopic quantum fluctuations to astronomical scales. Regions that were once in causal contact, able to exchange signals, were flung so far apart that they now lie far beyond one another's horizons. Our observable universe would then be one patch among many in a much larger domain, each patch starting with similar conditions imprinted by the same process. Whether inflation was eternal, producing an endless mosaic of pocket regions with potentially different microphysics, remains an open question. That broader multiverse idea is intriguing but speculative. The minimal testable content of inflation, the amplification of tiny fluctuations, the near flatness, the coherence of patterns in the microwave background, fits what we observe. On that reading, the cosmos that continues beyond our view is not foreign territory, but more of the same terrain. Even without inflation, we can test the assumption that what we see is typical. The cosmological principle, the hypothesis that the universe is homogeneous and isotropic on sufficiently large scales, has been remarkably successful. The microwave background is nearly the same temperature in all directions, once we remove the simple dipole from our own motion. The pattern of its tiny hot and cold spots matches the statistics expected from fluctuations seeded early and grown under gravity in an expanding background. Galaxy surveys that map millions of galaxies show that, beyond scales of a few 100 million light-years, the universe's structure looks statistically the same in different directions and places, aside from the expected growth with time. Peculiarities exist: local flows toward overdensities, vast underdense voids, the occasional especially long filament, but they sit atop a statistical uniformity. When those tests are turned into constraints, they say that if there are large deviations from homogeneity, they are too gentle or too distant to be seen within our horizon. The simplest reading is that the part we can see is not privileged. It is a fair sample of a greater whole. There is a limit to how precisely we can know that whole, and the limit is not just technical. It is built into the arithmetic of sampling a finite sky. On the largest angular scales, we have only one universe to observe and only one sky to average over. This limitation is called cosmic variance, the statistical uncertainty that remains when you have measured all there is to measure within your observable volume. It is an uncertainty of principle, not of instrument. Even a perfect telescope cannot reduce it. Cosmic variance reminds us that when we speak of what lies beyond, our claims must be probabilistic. They are extrapolations anchored to robust physics and supported by many independent observations, but they are extrapolations all the same. Hints about the unseen come indirectly. The pattern of galaxy clustering reveals that gravity has amplified initial fluctuations in ways consistent with the same rules across the sky and across time. The imprint of baryon acoustic oscillations, the frozen-in scale left by sound waves in the early plasma, appears with the same characteristic size wherever we look, acting as a standard ruler. That uniformity argues that the region beyond shares our physics and our history. The polarization of the microwave background carries signatures of scattering in the reionized universe, when the first sources lit up the intergalactic medium, and maps of that polarization distribution across the sky suggest a global story, not a local peculiarity. Gravitational lensing of the microwave background, the subtle smearing of its hot and cold spots by intervening mass, offers a consistency check on the growth of structure that reaches nearly to the edge of the observable. Each of these measurements traces long lines of sight through the cosmos and finds no contradiction to the view that the universe continues beyond our survey with similar composition and dynamics. Occasionally, debates flare about features that might signal departures from this uniformity. A curious cold spot in the microwave background, alignments among low-order multipoles, whispers of anisotropy in distant quasar polarization angles. Such hints are useful because they drive better catalogs and sharper analyses. So far, none has required rewriting the basic picture. In the handful of cases where a specific local structure, such as a large void, might explain an anomaly, the explanation lies well within known physics and within the portion of the universe we can already map. The horizon does not hide a fundamentally different cosmos in any way that the data demand. Topology offers another window onto beyond. If space were wrapped in a small, multiply-connected shape, like a three-dimensional analog of a torus, light could circle the universe and create repeated patterns. Matched circle searches in the microwave background have looked for exactly that, and their null results imply that if space is finite in such a way, its fundamental domain is larger than the observable region by a comfortable margin. This pushes any topological echo beyond our reach. Again, the conservative conclusion follows. What lies beyond is simply more space, with no tight fold that brings distant regions back into view. There is a human temptation to ask whether beyond might host exotic physics, different constants, different particle families, different laws. That temptation grows stronger if one entertains variants of inflation in which different patches realize different minima of some underlying energy landscape. At present, evidence for such variation is lacking. Measurements across vast distances place tight bounds on spatial changes in the fine structure constant and other parameters. Laboratory tests and astrophysical observations constrain the allowed departures heavily. The deep, durable insight is not that variety is impossible, but that the universe is astonishingly consistent. In the absence of compelling data to the contrary, the rational position is that the unseen continues the seen. The horizon's existence shapes our future knowledge. Because the expansion is accelerating, there is a maximum reach to what new light can bring. With time, the particle horizon will continue to grow, and some light emitted long ago from regions just beyond today's limit will arrive, adding detail to the edge of our map. In the same future, the event horizon will continue to withhold information from vast domains. Many galaxies already visible will drift, in a practical sense, out of view as their light is stretched into wavelengths too long to detect. The suite of empirical clues that let us reconstruct the early universe, microwave background, long baseline galaxy clustering, deep supernova surveys, will become harder to access for hypothetical observers living trillions of years from now in a bound island of merged galaxies. They will see a much smaller stage and may have no way to infer the wider play. The fact that we can still read the large-scale narrative is, in this sense, a temporary gift of our epoch. None of these limitations undermine the scientific content of the claim that the universe continues beyond what we can see. The rules that govern matter and light appear consistent across the vast distances and times we can probe. The geometry appears nearly flat, the distribution of structure statistically uniform on large scales, and the initial conditions inferred from one part of the sky match those inferred from another. Every line of evidence we possess says that our patch is not special. Beyond the horizon, the same physical book continues, even if we can turn only the pages that lie within our light cone. And for tonight, let that be enough. You do not need to hold the unseeable in your hands. Imagine the edge of your vision as a shoreline where light has finally arrived, and beyond it, a calm, continuing sea. Let your thoughts travel to that horizon and rest there, not straining to cross it, only acknowledging that more exists than you must grasp. Breathe slowly and allow the day's boundaries to feel gentle. The universe goes on, quietly, past the limit of sight. Within that quiet, there is room to sleep. Chapter 10. And yet you're here, a small awareness in a boundless cosmos. You have walked through stars and webs and widening space to arrive at a small fact. An awareness assembled from stellar atoms is reading these lines. Physics does not require awareness, yet it permits matter and energy to organize in ways that support it. Given time, gradients, and stable rules, complexity can appear without suspending those rules. A mind belongs here not as an exception, but as one lawful arrangement among many. From the universe to a person, the chain is continuous. After the hot beginning, the plasma cooled and electrons bound to nuclei. A near uniform sea of hydrogen and helium, dimpled by tiny ripples, filled space. Gravity amplified those ripples. Gas fell into dark matter wells and lit the first stars. Fusion built heavier elements. Winds and supernovae returned them to the gas. New clouds condensed with metals. Around young suns, disks whirled. Dust stuck, rocks merged, and planets took shape. On one such world, geology and chemistry produced conditions for metabolism and replication. By the Archean, isotopic fractionations in microfossils testify that microbes flourished. Oxygenic photosynthesis later changed the atmosphere, driving the great oxidation event and opening new pathways. Eukaryotic cells arose, very likely by symbiosis, incorporating once-free bacteria as mitochondria. Multicellularity followed. Development diversified. Extinctions pruned and resets refreshed the tree of life. Over deep time, lineages adapted to shifting seas and skies. From that history grows a brain that weighs about 1.5 kilograms and draws roughly 20 watts. It contains tens of billions of neurons supported by glia. Neurons maintain ionic gradients and use brief voltage pulses to propagate signals. At synapses, chemical messengers alter the probability that the next cell will fire. Synapses change with use. Networks therefore rewrite themselves as they operate. In that self-rewriting, information is encoded, predictions are compared with input, and behavior is selected. Biochemistry provides the substrate in a sentence. Carbon's valence, hydrogen bonding, water's polarity, and phosphorus chemistry make stable, flexible molecules. These regularities arise from quantum mechanics and the periodic table mapped onto nuclei forged in stars. Subjective experience rests ultimately on that chemistry playing out in warm, wet, self-maintaining cells. Consciousness, at least in part, is the integration of information about body and world into a coherent, reportable scene that can guide action. The integration is dynamic. Populations of neurons form transient coalitions that synchronize and exchange signals, then dissolve as conditions change. Attention biases the competition. Memory supplies priors. Valuation marks some inputs as urgent and others as ignorable. When you step outside and look up, activity rises in visual cortex. Regions that map space and value significance coordinate with systems that regulate the body. Motor systems prepare the next move. Energy flow constrains everything a mind can do. The body is a far from equilibrium system that must maintain ionic gradients, metabolite concentrations, and temperature by ingesting high-quality free energy and exporting heat and waste. Though small by mass, the brain consumes a large fraction of that budget because signaling and plasticity are metabolically expensive. Against astrophysical scales, 20 watts is nothing. Against a cell's accounting, it is constant labor. Awareness rides that flux. Placed back on the cosmic stage, one point stands out. Intelligent life could not plausibly have arisen very early. Heavy elements were scarce, violent transients were common, long-lived stable atmospheres were unlikely. As galaxies matured, metallicity rose, and catastrophic events became less frequent, creating neighborhoods where stars like the Sun and planets like Earth could persist for billions of years. That timing is a selection effect. Observers appear only where and when conditions allow. The brain compresses the vast into sketches that fit working memory and guide action. In a fraction of a second, photoreceptors transduce light, early visual areas extract features, higher areas attach meanings, and prefrontal networks decide whether to keep reading or dim the light. In minutes, you can outline processes that filled billions of years. In an hour, you can let that outline ease urgency. Knowledge accrues in layers. Physics supplies envelopes and constraints. Chemistry and biology fill those envelopes with mechanisms. Neuroscience connects mechanisms to function and behavior. Culture builds meanings on top of capacities. Awe does not flatten these layers into one vocabulary. It lets them coexist, each valid at its own scale and answerable to evidence. The cosmos does not assign duties. It offers conditions. On some nights, the air is transparent and a scattering of stars is visible. On others, there is cloud or city glow, and awareness is lit by memory and imagination. In either case, the link between you and the rest of the universe does not break. The calcium in your bones condensed in older stars. The iron in your blood was forged in supernovae. The oxygen you breathe came from ancient photosynthesis that remade Earth's atmosphere. Your body is a ledger of past physics written now. Science also counsels humility about what remains unknown. Consciousness has measurable correlates, rhythms, connectivity, metabolic demands. But first-person experience does not yet reduce neatly to a single theory. That is not a failure of physics or neuroscience. Explanation proceeds in layers, and higher-level regularities can be lawful without being derivable today from lower-level equations. Chemistry did not abolish biology, it grounded it. Neuroscience will not abolish subjectivity. It will map and predict its correlates more deeply. Consider the ordinary interface between your awareness and the universe. Photons from a page or screen reach the retina. Electrochemical waves propagate through layered circuits. Features are extracted and meanings attached. Language areas fire. Limbic systems mark some phrases as soothing and others as urgent. Frontal networks decide what to do next. The same physics that governs the redshifting of galaxies governs the ion channels that carry these signals. What does it mean to be small? Your body occupies negligible volume compared with a galaxy. Your lifespan is a brief pulse by stellar standards. But small is not the same as unimportant. Small systems can hold accurate models of larger ones and act with precision on scales that matter to them and to others like them. A nervous system can learn, teach, and repair. A person can rest, care, and choose. The universe will not notice those choices. The people near you will. For tonight, let gentleness work. The day has loaded working memory with half-finished tasks and half-parsed conversations. Let them drift to the edge of the workspace. The neurons will hum whether or not you consent. Rest gently. Breathe. Let breath lengthen now and soften gently. Notice gravity's pull on the body and allow it to be sufficient. Close your eyes. Photons will still cross their gulfs. Galaxies will still drift with the slow widening of space. Stars will still burn with patient steadiness. In your chest, the heart will keep its rhythm. In your head, spontaneous activity will reshape into the slow waves of sleep. Nothing more is required. You are here, small and aware, in a cosmos vast and unaware. And that contrast is not a problem to solve. It is a place to rest. My friend, we've reached the end of our journey for tonight. The stars, galaxies, and horizons of the universe will continue their dance, and you can let that thought bring you peace. If you're still awake and curious, I invite you to explore another video. There's always more of the cosmos to wander through. But if your eyes are closing, then let go and drift into sleep. Sweet dreams among the stars.